Section: Introduction. In this section, we explore the idea that compression and intelligence are closely linked, a concept that has been discussed by researchers for a long time. Recent advancements in large language models, LLMs, have further fueled this discussion, prompting us to investigate language modeling from a compression perspective. According to compression theory, any predictive model can be seen as a lossless compressor, and vice versa. This means that language modeling can be viewed as a form of compression, with LLMs demonstrating strong data compression abilities in practice. Despite these theoretical discussions, there is limited empirical evidence on the connection between compression and intelligence. Our goal is to fill this gap by answering the question: does a language model's ability to encode a text corpus using fewer bits in a lossless manner indicate higher intelligence? We define intelligence in a practical sense, focusing on the model's performance in various tasks rather than delving into philosophical definitions. We measure intelligence based on three key abilities: knowledge and common sense, coding, and mathematical reasoning. To assess this, we gather raw data from different domains, e.g., GitHub code for coding ability, and evaluate how efficiently various LLMs can compress this data. We then test these models on a range of tasks to evaluate their domain-specific intelligence using benchmark scores. Our aim is to investigate the relationship between a model's compression efficiency and its performance in downstream tasks. Through experiments involving 30 public LLMs and 12 diverse benchmarks, we make a significant discovery. There is a strong linear correlation between LLM's compression efficiency and its performance in downstream tasks, with a Pearson correlation coefficient of approximately -0.95 for each intelligence domain evaluated. This linear relationship holds true even for individual benchmarks. While previous studies have explored the relationship between benchmark scores and validation loss within the same model series, our study is the first to establish a linear correlation between compression and intelligence across various model characteristics. This finding supports the idea that superior compression is a sign of higher intelligence in LLMs. From a practical standpoint, using compression efficiency as a metric for evaluating LLMs can help prevent overfitting and test contamination. We provide our compression corpora, data collection, and processing pipelines as open-source resources for future research. Section Summary. In this section, we explore the connection between compression and intelligence, particularly in the context of large language models, LLMs. We investigate how language modeling can be viewed as a form of compression, with LLMs demonstrating strong data compression capabilities. Our empirical study reveals a linear correlation between LLMs' compression efficiency and their downstream task performance, supporting the idea that superior compression is indicative of greater intelligence in LLMs. Section: Examining Compression and Intelligence, the Experimental Protocols. In this section, we aim to empirically explore the connection between compression and intelligence in the realm of large language models. Our approach involves studying various pre-trained LLMs of different sizes and origins to evaluate their compression effectiveness and intelligence. Our objective is to summarize the potential link between compression and intelligence based on our assessment findings. To ensure the generalizability of our conclusions, we gather diverse LLMs created using different training data, tokenizers, computation methods, and architectures. We begin by detailing our experimental procedures for evaluating both compression and intelligence. When it comes to assessing intelligence in LLMs, there have been ongoing debates about its definition. While the Turing test has been a widely accepted measure, it has limitations due to its reliance on subjective judgment. More recently, a concept called universal intelligence has been proposed, focusing on an agent's ability to achieve goals across various scenarios. In our evaluation, we measure intelligence based on the model's performance across multiple tasks, including knowledge, common sense, coding, and mathematical reasoning. For evaluating the compression of LLMs, we use the average bits per character, BPC, as a metric to gauge compression efficiency. This metric accounts for the different tokenizers used by various LLMs. Additionally, We standardize the context window size to 1900 tokens across all evaluations to ensure consistency in information access during compression and task execution. We concentrate on base models rather than fine-tuned models, as the latter are considered specialized for specific data types and may not exhibit general compression abilities. Our focus is on short to medium context scenarios, leaving the exploration of long context scenarios for future research. Section Summary. In this section, we empirically examine the relationship between compression and intelligence in large language models by investigating various pre-trained models of different sizes and origins. Our goal is to summarize how compression efficiency and intelligence are related based on our evaluation results, using diverse models created with varying training data, tokenizers, computation, and architectures to ensure our conclusions are general and not specific to particular model series. We define intelligence based on an agent's ability to achieve goals across different scenarios and evaluate it in LLMs through average performance across multiple downstream tasks, while assessing compression efficiency using the average bits per character metric and unifying context window sizes to ensure consistency in model evaluation. Section: Compression Corpus. In this section, we will discuss how we selected the corpora for measuring the compression of models. We understand that different corpora can highlight different aspects of models' abilities, and being good at compressing one corpus may not mean being good at compressing another. Therefore, we chose corpora that align with our focus areas and do not overlap with the model's pre-training data to prevent data leakage. Since the pre-training datasets of large language models, LLMs, are not transparent, we decided to use the latest corpora for evaluation. Specifically, we gathered texts from the most recent Common Crawl dataset to assess knowledge and common sense. For coding ability evaluation, we collected data from GitHub repositories, mainly focusing on Python language due to downstream benchmarks emphasizing Python coding skills. To evaluate mathematical reasoning, we selected academic papers from arXiv, specifically those categorized as math. We made sure to use the most up-to-date data for each source during our experiments. Details of our compression corpora composition can be found in the table, and more information on data collection and processing is available in the appendix. Moving on to overfitting benchmarks, we acknowledge that LLMs can become overly optimized towards specific benchmarks, making benchmark scores unreliable indicators of intelligence. For instance, adding multi-choice QA training data can significantly boost performance on multi-choice QA benchmarks like MMLU, while showing no improvement on general QA benchmarks like Trivia QA. In the math domain, some models excel on benchmarks like GSM-8K and math but struggle on new math tests. In such cases, benchmark scores may not accurately reflect the model's intelligence in that area. Although our focus is on base models in this study, where overfitting may be less common, some LLMs could still be trained specifically on benchmark data during pre-training or even face test data contamination issues. To detect such cases, we use the min-k%prob method to identify if a given text was part of the model's pre-training data. This method calculates the average negative log likelihood of selected tokens in a text example to determine pre-training exposure. In our experiments, we compute the min-k% score for all test splits of benchmarks and, if available, for training splits as well. We will highlight and discuss LLMs with unusually high min-k% scores, using a value of 20 for k as suggested. In our general setup, we aim to explore the relationship between compression efficiency and intelligence using 8 series of general-purpose language models, including diverse organizations and varying sizes. Alongside dense transformer models, we introduce Mixtral 8x7b, which employs a sparse mixture of experts, (MO) architecture. Additionally, we incorporate cutting-edge models specialized in coding and mathematical reasoning, focusing on general-purpose LLMs across all benchmarks, code LLMs in coding areas, and mathematical LLMs in mathematical reasoning areas. Our investigation centers on well-trained LLMs, where their intelligence is likely already evident, unlike models still in the optimization phase that may perform poorly and yield noisy results. Models are evaluated consistently using few-shot in context learning or zero-shot methods following benchmark norms, ensuring a fair comparison with the same codebase. Further evaluation details can be found in the appendix. Regarding metrics, we use bits per character, BPC, to evaluate compression efficiency and calculate the Pearson correlation coefficient, Pearson rho, between average benchmark scores and BPC to quantify the intelligence compression correlation. We conduct a linear fit between average benchmark scores and BPC, reporting the root mean square error, RMSEE, to measure how much models' benchmark scores deviate from the linear prediction on average. This analysis extends to individual benchmarks, and we visually represent the relationship through linear regression plots, with each model represented as a point in the graph. Section Summary. In this section, we select compression corpora aligned with our focus areas, such as Common Crawl for knowledge and common sense, GitHub repositories for coding ability in Python, and archive papers for mathematical reasoning. We aim to avoid overfitting by assessing ILM's performance on various benchmarks, as some models may overoptimize towards specific benchmarks, leading to unreliable intelligence representation. By using the min-k%prob method, we detect potential data exposure during pre-training, ensuring a fair evaluation of LLMs across different benchmarks and models. Section: Overall Intelligence versus Compression. In this section, we have summarized our main findings by examining the relationship between overall intelligence and compression efficiency. We calculated the average benchmark scores across all three areas and the average BPC across all compression corpora. Our analysis revealed a strong linear correlation between the average score and the average BPC, supported by a Pearson correlation coefficient of -0.94 and an RMSE of 2.8%. This linear relationship is significant despite the variability in evaluating downstream benchmarks due to factors like prompts and decoding hyperparameters. We also delved into the results for the three key areas individually, showcasing similar qualitative and quantitative patterns. Previous studies have focused on correlating benchmark scores with validation losses in constrained settings, whereas our work breaks free from these constraints by comparing models with diverse tokenizers, designs, and pre-training data. Our results establish a universal linear correlation between compression efficiency and intelligence. Furthermore, we present detailed results for the knowledge and common sense area, revealing a strong linear correlation between individual benchmark scores and compression efficiency. Minor fluctuations in evaluation details can explain slight variations in accuracy. We observed differences in the linear correlation among benchmarks like Hella Swag, Trivia QA, and MMLU, attributing them to factors like performance saturation and dataset mismatch. Similarly, in the coding area, we found a robust linear correlation between compression efficiency and coding ability across different architectures. The MO model, Mixtral 8x7b, aligned well with this correlation, particularly excelling in the DS1000 benchmark. The DeepSeek Coder models consistently outperformed the linear fit, possibly due to exposure to task-specific data during pre-training. In the mathematical reasoning area, we noticed similar correlation trends, with a focus on addressing overfitting benchmarks. By computing min-k% scores for each example, we identified potential exposure to pre-training data in certain models. The Quen model series stood out as outliers, achieving higher accuracies than predicted, possibly due to exposure to specific training and test data during pre-training. Overall, our findings highlight a strong linear correlation between single benchmark scores and compression efficiency, challenging the notion that individual scores are too noisy to reflect general model ability. Section Summary. In this section, we have analyzed the relationship between overall intelligence and compression efficiency across various benchmarks. Our results show a strong linear correlation between average benchmark scores and bits per character, BPC, across different compression corpora, with a Pearson correlation coefficient of -0.94 and an RMSE of 2.8%. Additionally, we have delved into specific areas like knowledge and common sense, coding, and mathematical reasoning, observing consistent linear correlations between compression efficiency and model performance in each domain. Section: How does different compression corpus influence the linear relationship? In this section, we explored how different compression corpora can impact the linear relationship. In our previous experiments, we deliberately chose compression corpora that matched the specific area of interest. Here, we delved deeper into the effects of using various compression corpora on the outcomes. We looked at two cases where the compression corpus did not align well with the particular domain, comparing compression on common crawl data with mathematical reasoning benchmarks, and comparing compression on GitHub code data with knowledge and common sense benchmarks. The results, shown in a figure, revealed that when there is a significant mismatch between the compression corpus and the benchmarks, the linear correlation is notably weaker compared to when using in-domain data. These instances, along with the MMLU case discussed in the appendix, highlight the importance of having a good match between the compression corpus and the specific area of study for a strong linear correlation. However, it's worth noting that our previous findings remain quite robust because the compression corpora we selected rely on simple rules at a broad level without intricate design. Identifying the most suitable compression corpus that aligns well with specific benchmarks automatically is a crucial challenge that we leave for future research. We also investigated the number of characters needed to reliably compute BPC. For instance, we studied how the size of the compression corpus affects knowledge and common sense abilities. By varying the number of characters in the compression corpus from 50K to 100M, we observed changes in the Pearson correlation coefficient and the RMSE, as shown in a figure. As we increased the number of sampled characters, the linear correlation gradually strengthened and eventually plateaued around 30M characters. This suggests that a compression corpus with tens of millions of characters is sufficiently large. We also discussed the impact of random sampling on compression evaluation in the appendix. Furthermore, we considered extending our experiments to tasks that require abilities in multiple domains, not just a single one. For example, tasks that involve both coding and mathematical reasoning. By using the Program-Aided Math Reasoning (PAL) method on GSM-8K, which combines Python and archive math corpora to create a mixed corpus that aligns with these abilities, we found that this mixed corpus showed a stronger linear correlation compared to using either corpus alone. Our research findings support the idea that better compression reflects higher intelligence. We suggest using compression efficiency as an unsupervised, adaptable, and reliable metric to evaluate ILM's capabilities. The flexibility in updating and composing the compression corpus helps avoid issues like data contamination and benchmark overfitting that often plague evaluations. While previous work has introduced various corpora for evaluating LLMs with losses, our study provides empirical evidence by showing the correlation with intelligence. However, our study has some limitations. We focused only on base models as fine-tuned models are not general-purpose compressors for any text. Yet, we believe there are interesting connections to explore between base model compression efficiency and benchmark scores of corresponding fine-tuned models. We initially found evidence of this correlation in mathematical reasoning ability, albeit limited to llama models. Additionally, our focus was on short to medium context scenarios, deferring the examination of long context situations. Lastly, our conclusions and findings may apply only to well-trained models and may not hold for language models where the evaluated abilities have not fully developed. These are areas we aim to investigate in future studies. We are grateful to Graham Neubig, Yao Fu, and Pengcheng Yin for their valuable feedback on this draft.